This is a typical multi-stage centrifugal compressor with its corresponding cut-section view. Having previously discussed performance characteristics of a single compressor stage, we will now examine the effects that multi-stage compressor configurations have on the overall compressor performance curve. Recall that the stage curve is defined as the curve representing the performance of one stage. And this is for reminder what the compressor stage looks like. Recall that a compressor stage consists of the impeller, the stage seals, the diffuser, the crossover, and return passage. Each compressor impeller stage has a specific performance curve that is plotted as actual volume flow versus head, as depicted here, and actual volume flow versus efficiency. The amount of impeller stage head is limited by both mechanical and aerodynamic factors. Mechanical factors include impeller stresses and blade natural frequencies. Aerodynamic factors are tip speed, optimum efficiency, Mach number, and flow range considerations. We'll see this in details further ahead. Now, a compressor section is defined as the number of stages between the compressor case and nozzles. Referring back to our previous example, the compressor section is highlighted. A section can contain one or more stages. In our example here, as you can see, it contains 5 stages. The performance of the section is defined by the section curve, and the number of stages per section is limited by the discharge temperature, process gas characteristics, compressor casing and configuration, and rotor stiffness. In this section, we will examine stage and section performance for an ideal designed compressor case, a case with fouled impellers, and a case with varying molecular weight. Any multi-stage compressor is designed on the basis that succeeding impellers will compress a lower volume flow resulting from the compressibility of the specific gas handled. Remembering that each application is designed for only one operating point, the compressor designer matches each successive impeller as closely as possible to achieve operation at the individual impeller design point, such that each individual impeller will operate at its best efficiency point. It is important to understand here that in many applications, operating at the compressor section rated point does not mean operating at each individual compressor impeller best efficiency. Many older design multi-stage compressors were built using specific impeller designs. For any given application, the succeeding impeller may not be at its optimum efficiency point, but may be significantly far from that operating point. A good rule of thumb in selecting a multi-stage compressor is to make sure that when operating at the compressor section rated point, each impeller operates at approximately plus or minus 10% of its design point. Today, almost all compressor manufacturers are using computer design to manufacture each impeller individually, so that each impeller operates at its design point, and so there is a minimum of mismatch between impellers. Therefore, it can be seen that the overall performance section curve is the composite of the operation of each individual impeller performance curve. If the performance of one or more of the impeller stages in the compressor section were to deteriorate as a result of fouling or increased labyrinth seal clearances, the overall performance curve will be affected. The amount of this effect will depend on the performance deterioration of the individual impeller stages. We will see a case where the first and second impellers of a three-stage compressor section become fouled. The resulting section operating curve can deteriorate in a significant way in the terms of head, flow range, and efficiency. Another case that we will consider in this section is the change in gas molecular weight. Remember that once an impeller is designed, its energy production or its head production at a given flow point is essentially fixed. We will see that pressure rise will change as gas composition changes. Remember that each gas composition requires a different amount of head to increase its pressure level to a given amount. An impeller or blade is designed for only one gas composition, and therefore only a specific amount of head is designed in a blade or impeller for a given application at a specific flow rate. In a multi-stage compressor, the effect of gas composition change can have a significant effect on the overall compressor curve. If, for instance, a gas of higher molecular weight were to be handled, the pressure produced in the first stage of a multi-stage compressor section would increase. Since the gas is compressible, this would result in a reduced volume to the second stage. This impeller was initially designed for a higher volume, but now will handle a lower volume. Also, a dynamic blade or impeller will produce higher energy or head at a reduced flow, therefore compounding the effect of the molecular weight increase with increased blade energy capability, resulting in a further reduction in flow rate to the succeeding stage. This fact will result in a shifting of the section curve from the design point towards the surge point, as depicted here. And this phenomena could result in surge of a compressor with no significant change in system resistance. This will be explained in details in the next couple of videos. Most of the dynamic compressors used today are multi-stage because the head required by most processes are in excess of the head produced by one stage of a dynamic compressor. Typical values for one stage of dynamic compression are as follows. In the case of a centrifugal closed impeller, the head can reach 10,000 feet. In the case of a centrifugal open impeller, the head can be in the range of 15,000 to 25,000 feet. And in the case of axial blade row, the head can reach 3,000 feet. The following figure shows for reminder the components associated with one stage of a centrifugal closed impeller. Recall, we have seen this in details in a previous section. A typical stage consists of an impeller, stage seals, namely the eye seal and the shaft seal, of a diffuser, a crossover, and return passage or inlet to the succeeding stage. For each impeller or blade stage, there exists a specific performance curve. In order to achieve maximum efficiency and flow range in a multi-stage dynamic compressor, each stage should be operating at its maximum efficiency point when the compressor is at its rated point. This is not true for many older designs where only a limited number of compressor impeller or blade designs were available to select from. Be aware that the amount of head produced by one stage is limited by certain mechanical and aerodynamic factors. The mechanical factors include the impeller stresses and the blade natural frequencies. Aerodynamic factors are tip speed, optimum efficiency, Mach number, and flow range considerations. There will be more about this in a later video. But for now, as a concrete example, open impellers can produce as much as 250% greater head than a closed impeller, because the impeller stresses at higher speeds are reduced in a significant way by omitting the impeller cover or side plate in the case of an open impeller design. Frequently, there is much confusion concerning the terms compressor stage and compressor section. Process engineers and operators usually use the term stage to describe what properly is termed a compressor section. This is probably because process flow diagrams only show a stage and not the individual impellers in the usual block diagram format. A compressor section is defined as the number of stages between compressor casing nozzles. In this cut-section view of a typical multi-stage centrifugal compressor, the compressor section is highlighted here. A section can contain one or more stages, and its performance is defined by the section curve. Here you can take a closer look at this compressor section, with the casing and other internals removed. As you can see here, in our example, this compressor section contains 5 stages. Now, in order to properly define compressor performance, a performance curve is required for each section, as depicted here. Each sectional performance curve is developed from the individual impeller stage curves. An important fact to remember here concerning compressors is that the design of each succeeding stage is based on the predicted preceding stage performance. If the preceding stage performance is not as predicted, the next stage will be affected. And of course, the greater the number of stages, the greater this effect will be. It is commonly called in the industry mismatching. Any change in gas density, pressure, molecular weight, temperature or compressibility will affect the flow into the succeeding stage and thus affect the performance. The most effective way to minimize the effect of mismatching is to require that each compressor stage operate as close as possible to its design or best efficiency point. The number of stages per section for dynamic compressors are also limited by performance and mechanical factors. And these factors include discharge temperature, process gas characteristics, casing configuration, and rotor stiffness. Some processes can cause accumulation of solid materials or fouling within the compressor impellers or stationary passages. Such a phenomena is usually temperature-related and can influence the number of intercooled sections for a given application. Also, a large number of stages on a single rotor can reduce the rotor stiffness and thus reduce the natural frequency of the compressor. As previously discussed, the performance curve for any compressor section is derived from the individual stage curves of each impeller in that section. The following figure shows an example of a 3-stage nitrogen compressor section. Here you have the individual performance curve for the first stage, the second stage, and the third stage. And here the overall performance curve or the section performance curve. Note here how the inlet volume flow to each successive stage is reduced, and how it depends on the impeller head produced by the preceding stage. Now I'm going to show you the effect of fouling the first and second stage impellers in the same compressor. So, in the fault condition, the head capacity curve and the efficiency curve for the first stage will look like this. And for the second stage, they would look like this. Note here how this affects the operating points on the third stage, with the new operating points in fault condition. So, reduced head with increasing flow and reduced efficiency. The same effect would occur if the interstage labyrinth clearance increased from erosion or vibration on the first and second stages. Any reduction of head produced in a preceding stage will increase the volume flow in a succeeding stage, and therefore reduce the overall head produced by a compressor section, as depicted here. Let's now get back to a state of clean impeller condition. And let's observe the effect of changing the molecular weight in the same compressor. In the initial state, the gas processed is nitrogen, with a molecular weight of 28. Let's now assume a gas with a higher molecular weight, let's say 32. The head capacity curve corresponding to the new gas of the section performance curve will look like this. So, as you can see, the greater the molecular weight, or in other words, the greater the density of the gas, the greater the discharge pressure, and the closer the surge point to the design point. This is due to the fact that once any dynamic compressor stage is designed, the head produced for a given flow and speed is fixed. The greater the density of the gas, the higher the pressure produced, and the lower the volume flow. Flow is inversely proportional to pressure. So, since surge is caused by low flow, then a dynamic compressor handling a denser gas will surge sooner. Now, in the case of a reduced molecular weight or gas density, as seen here, the opposite effect will occur. The discharge pressure will be reduced, and the surge point will move to the left, farther from the design point. This concludes the section concerning individual stage and overall performance. One last thing I want you to know before moving on to the next video is that individual stage performance curves are vendor proprietary information and are not reproduced. The only opportunity that you have to review these curves are prior to an order or during a design audit. So, I strongly advise you to review this information during the bid phase of a contract to determine if all individual impeller operating points, when operating at the rated point, are as close as possible to the individual impeller best efficiency points.